So now we've talked about the electrostatics when we have charges just floating around in space. One up here and one here, maybe a rod down here, maybe a plane over there. But now we want to think about something more realistic. We want to think about charges in materials and how materials behave in terms of electrostatics. So there are many, many materials in the world that do many, many amazing things. But for the electrostatics in freshman physics, we can basically narrow it down to just two kinds of materials. So let's look at charge in materials. So we can narrow it down simply to insulators and conductors. So what goes on in an insulator? Basically, all you need to know is that the electrons are bound to their atom. They're not free. So if we think about the inside of an insulator, we can imagine that the atoms, the nuclei of the atoms, are arranged in some way, maybe like this. And the electrons are stuck with their atom. So they're going around in a cloud like that, and they can't leave. And I've drawn way too many of them. Now it is true they can interact. So a chemical bond is these two electrons talking to each other. So there can be forces between them, and they can create bonds, but they can't really go anywhere. All right? They get a little bit electrostatically interesting because their surface is sticky. Like in the Teflon rod, we know the electrons can't go anywhere, but if we rub the surface, we can put extra electrons on the surface and we can give it a surface charge. That's how we can see electrostatic phenomenon. Or we could rub it a different way and remove charge from the surface and lower the charge and make this side essentially positive. So you can play a little bit with insulators, but basically the charges don't move. The other kind of material is the conductors. Now, you can make conductors a few different ways. So the ones I'm going to talk about are metallic conductors. Okay. The example I'm going to give, the definition I'm going to give applies to metals. And throughout the class, I will say metals a lot. And when I just say metal, I really just mean metallic conductor. Okay. So in a metallic conductor, the electrons move freely throughout the material. Okay, so if I were to draw a metal like this, here's your atoms, like that, and I left out one word, some electrons move freely through the material. So some of the electrons are still bound, just like they were in the insulator. These electrons do not leave their nucleus, but then some are just free to wander around. They can go visit this atom for a while, see how it's going, and then go see this atom, and send a message over to this atom about this atom's parents. So they can go all through the material and flow around. Okay? Because the charges are free to move, that allows a lot of different things to happen, as you can imagine. So you can actually think of this motion, you can actually kind of treat it as a gas. You can actually get pretty far in physics in figuring out the properties of a metal just by treating it as a gas of electrons. But eventually you run into trouble because there's this thing called quantum mechanics that ultimately makes it not behave like a simple gas. Okay, so then moving forward, now that we have these two materials, we're going to come up with new ways to charge things up other than rubbing cats and stuff like that. Okay. Well, we do have a question before we keep going. Let's see. So let's see. JVJ24601. So are all conductors charged? Let's see. Okay. Yeah. No. Okay. Yeah, so the question is, are all conductors charged, right? So I have described these kind of different. Here you've got the regular situation. Here's an atom. The atom is neutral. It's got protons here, electrons here, the same number. It's also true here. The protons are positive, the electrons are negative, but some of the electrons are stuck, but they're not enough to counteract the charge of the proton. So you need these free electrons to make the thing neutral. So the answer is no, the metallic conductor is not charged. It's still neutral. It's just some of the electrons that make it neutral are free to move around. So we still have the same number of protons and electrons. There's not any extra electrons. It's just the way the chemical bonding works out, some of them are free to move around. This also is relevant because it's neutral. What this is also explains why the electrons don't leave the material. So if one of the electrons said, I'm going to come out here and spin around, that would actually leave the thing positive. It was neutral, we took away an electron, now it's positive. So if this thing is positive and this is a little electron, it's going to be sucked right back in. So the material, the positive nuclei of the material act like sort of like a box or an energy well for the electrons. And they can move around, but they have to stay in the material. We've talked about charging objects up by rubbing them, but we need another way. We are now going to talk about charging by induction. This is something we can do now that we know we have two kinds of materials. So one material will be our charged insulator. It could be the Teflon rod. So we know if we take the Teflon rod and we rub it with the fur, we get negative charge on the surface. So the insulator gives us a way to just hold a charge somewhere. Now the other object that we want to bring nearby is a neutral conductor. And as you know, when I talk about a conductor, I almost always talk about a metal. So let's assume this one is a metal. So now, since it's a metal, we'll think microscopically what's happening inside. So we know in this metal, it's full of free electrons. Say here's an electron, it's got a negative charge, it's just sitting there minding its own business. However, we bring this charged insulator nearby, all these negative charges. It's going to feel a force due to Coulomb's law. It's going to feel a force this way. So it's going to accelerate that way, it's going to move that way, and it wants to get as far away as it can from these. It's always going to feel a force. It's going to go until it gets right here. And then it can't go any further because it can't leave the material. Now, what's left here though? Let's think for a second. What's left here? What's left here is a place where there used to be an electron, and now it's missing. So that nucleus, that atom, is net positive. So you actually leave what we call in physics often, we call it a hole in the material, in the metal. It's a place where the electron was to keep things neutral, now it's gone. Well, that hole isn't just going to sit there. You can think of that hole as a positively charged particle. Actually, you could imagine that hole is a positively charged particle that's going to come over here. Or you can say these free electrons, they want to get away too, but if they move a while, they might see that hole. And they'll say, oh, okay, I'm going to go there. And that's going to take that thing away, but now we have a hole here. So you can think about imaginary positive particles called holes. You can imagine refilling the holes left by the electron that moved. You can think about it however you want. Ultimately, though, you get positive charge on this side. Okay? It was neutral. You move some excess charge over here. You leave positive charge over there. And a bunch of charges will do this. A bunch over there, a bunch will build up opposite amount over here. So now this conductor is polarized, is what we would say. The charge has been polarized. It's been pushed to the two poles. We have a negative charge over here, positive charge over here. So now, to charge by induction, all we have to do is one thing. We cut it. With the negative, or with the negatively charged insulator here, we just cut it in half. So let's cut it in half into two pieces of metal. And this is still here. Okay. So the charges don't have any need to go anywhere. They're happy where they are. But because of the way it's all set up, and with this still here, you end up with positive here and negative here. Okay. All we did was make an imaginary cut right in the middle. And now, though, you can see, even when this is gone, now each half, oops, has equal and opposite charge. So now they're both charged. In fact, we charged up two things. We charged up this piece of metal positive and that piece of metal negative. Now in the real world, you don't charge by induction by cutting pieces of metal. Cutting metal is very hard. There's other ways that you do it. Here in this demo, we're going to charge these two spheres by induction. So the two spheres are the piece of metal. And we have them touching right now. And electrons can easily move from one to the other when they're touching. So it's essentially one piece of metal. But later when we move them, that's a way to cut them. We don't really have to cut them. We just have to separate them like that. But when they're touching, the conductance across that gap is pretty good. So we think of it as one piece of metal. I'm going to bring my Teflon rod, charge it with fur, bring it close, and it's going to create a separation of the two charges, or of the charge in the metal. So if I do this, here's a negative charge, I bring it right here. It's pushing negative charge over here, and it's leaving positive charge over there. Right? You didn't see anything. Well, there's nothing to see. Right? So let me charge it up again, bring it over here, and now I'm going to cut. I'm going to separate them. And now we just charge the two spheres by induction. And of course, you can't see it. I'm going to try to prove it to you with a little bit of Teflon tape. Right? So we know if we rub fur on this Teflon tape, we know it ends up negative. So if this thing ends up negative, then they should repel each other, or the tape should be repelled. And sure enough, you can see the tape is repelled. Doesn't want to touch the metal. And we should have left the other one positive. Oh, and sure enough, it's positive. It's very sticky for the tape. Okay? So we can use our Teflon rod, or our Teflon tape, to confirm it really did what it was supposed to do. Repulsion there. There's one other way we can confirm it, is when I bring them together, if you look very close, you can see a spark jump across the gap. The negative charge, the positive charge comes back together, makes a corona and an arc like we talked about before, and you can actually see the charge go back. So seeing is believing. And there it was. Okay, so charging by induction. It's also not a quantitative thing like rubbing. We aren't going to calculate the amount of charge that we pushed around. Maybe we can do that later. But for now, it's just another way to think about how charge behaves in a material. Charging by induction illustrates an important topic in circuits, actually. Let's charge by induction with something large. We did it with two aluminum spheres that are about the same size. Let's think about doing it another way. What if we have our Teflon rod here, right? And let's have one of our aluminum spheres here. Okay. Well, we know what's going to happen to that single piece of metal. Electrons are going to run and hide over here, leaving that side kind of positive. We're going to polarize this thing. So this is our insulator that's charged, and this is our conductor that is now polarized. So rather than cut, what we really did is we had another aluminum sphere touching it. So we actually had this, they were touching, the electrons were actually over here, and we pulled it apart. Okay? But what if we did it with something large? What if instead of another aluminum sphere the same size, what if it touched a huge aluminum sphere like this? Would it help? Would it be any different? I don't know. You might actually get a little bit more charge on it, because now this can go away. It goes even further away. Maybe you leave more of the area charged. So you can kind of imagine it might be better to touch it to something large. So to see if you can do this with something larger, we need a large conductor. So let's think. This is the biggest aluminum sphere I have. I don't have any other big aluminum spheres on me at the moment, but I do have one other big conductor, and that's me. You are a conductor, not that conductor. You are a conductor in the terms of sort of a salt water, right? So if you have a solution of salt, the salt breaks down into sodium and chloride ions if it's table salt, and those ions can move around in the water. So you have mobile charges in salt water. So salt water is a conductor. Not as good as a metal, but it's still a conductor. So in terms of electrostatics, your body is basically a leaky bag of salt water. It's full of this salty sort of gel, your skin is moist, you're basically salt water. So you are a conductor. So what I can actually do is make myself the other conductor. So we charge up the rod, and I put my finger here, and then I bring the rod here, and you might worry that I'm making a circuit, but nothing flows along the rod, so it's okay. I just pull my finger away, and that charges up the rod. Let's see if it worked. So remember, let's see, that should have left the rod what? It should have left the rod positive, because we pushed the negative charge into me. So now this negatively charged tape should be attracted to it, and sure enough, it's a positively charged piece of aluminum. Everywhere you go, it's got positive charge on it. Fairly strong, actually. And the reason it's strong is because I'm big. I'm bigger than that other sphere. We can get a lot of charge. In fact, the way you usually do this is you don't sort of have to be touching it and break contact. Often if somebody's going to charge something by induction, it's almost like a parlor trick. You almost have to watch quickly to see them do it. So you bring this here and you just touch it like that, and now it's charged. Just with that brief touch, you picked up the negative charge that was pushed to this side. Let me try it one more time, because if I do it and get a little closer, you'll probably even hear the spark. You can hear the charge jumping into my finger. So we get a little close to the mic here. We're polarizing it, and now I'm going to accept the charge. So maybe you heard that. And now it's going to be very highly charged. Like that, see? Really wants to touch it. So I'm large, I'm a big conductor, but there is yet one other big conductor that you always have access to, almost always have access to. And that would be a really large conductor, the Earth. Okay? Not to scale. If you go deep enough in the ground, it's sort of wet dirt, and wet dirt is a good conductor. It's sort of a liquidy, jelly thing full of ions. So if you touch things to the ground, you can discharge them. Or you can think of it this way, is current or charge will flow into the earth from something charged up. And when we get into circuits, you're going to know that the flow of charge is current. This is why circuits are always grounded. We say grounded, it actually really means something. The symbol that means ground in a circuit, which you know or you'll learn about, really means ground. It means eventually when you build a building somewhere, there's a rod that has been dug straight into the ground, really deep, and that's where all the circuits in the building eventually have to go. They also use the plumbing, so there's other ways to do it. But building code does require an actual ground rod for buildings. So that's why we say ground. We really do mean the earth. And it really, you can first understand it by charging by induction.